Hello. Hi, friends. So I'm Emily. I'm an undergrad at the University of British Columbia and software developer, and you can reach me at hello@emily.ma. I've recently had the privilege of working with Professors Clayton D'Souza, Dongwook Yoon, and Ivan Beshesnik at UBC on the topic of understanding open source collaboration empirically in the real world. We analyzed over 50 large open source projects hosted on GitHub and developed a novel graph-based perspective that we're calling the GitHub PR issue graph. We found that there's a lot of unspoken context and hidden patterns in collaboration that GitHub and other developer platforms don't highlight. And today I'll be showing you how we revealed them. I'll be covering the novel workflow patterns that we found, how we identified them with Neo4j and Cypher, and this PR issues graph's attributes as well as its implications. You'll walk away with a new outlook on open source collaboration, able to identify common workflow patterns and understand what they might mean for your community and project. I hope this talk will serve to spark some brainstorming and discussion around how we can be more mindful of these workflow types as we participate in open source development efforts. As many of you might already know, GitHub is a developer platform built on top of the version control software Git. It's a popular choice among open source projects as a central platform for collaboration. So on GitHub, community bug reports, feature requests, and general discussion about projects are done on what we are called issues. I'd like to highlight that issues have a designated status. So you can see that on the left here that this issue is open, which means that the bug that's being reported in it or the feature request hasn't been addressed yet. And you can see in the issue on the right that the issue is closed, which means that it's been fixed or the discussion has been deemed off-topic or closed. And new code, perhaps addressing those previous issues, are merged into projects on GitHub via pull requests. These also have statuses, so they might be open if the project is the work is undergoing or will undergo code review. Might be closed if the work was deemed unsatisfactory or extraneous, and it might be merged if the work was accepted and integrated into the project. People discuss and review code in these pull requests. And another feature they have is that you can create links between issues in a PR. For example, if this PR, which is fixing some other mentioned issue, so this PR is 8156, and the developer has put closes 8150, creating this explicit connection between the two. So that's kind of the GitHub backstory and the context on the different parts of GitHub's model, but I wanted to talk more about these particular links in between issues and PR, which are a hot topic in software engineering research. So here, as I've shown you, this PR on the left, that this is a fix for some bug, and it mentions, again, that closes 8150, which is referencing this issue on the right. So GitHub actually has two types of links. So they can be either fixes, as seen here, as closes is one of the fixes keywords, or duplicates. And if you mention a keyword associated with either the fixes or duplicate link type, as well as an issue number, as the developer on the left here has done, GitHub will automatically create a link in the UI with the appropriate type. If we frame this as a collaboration graph for a second, something basic but interesting starts to emerge. If we consider these PRs and issues as nodes in a graph, and the links between them as edges, this is kind of what we can visualize here. So we can model the node type, so issue or PR with a different shape, so a circle for a PR and a square for an issue, as well as the node status with some colors. So for our work, we'll be using purple for merge, green for open, and red for closed, just like on the GitHub UI. So again, this is the exact same example I've been showing in the previous slides. We have that PR 8156, which is merged, connected by this fixes link as expressed on the GitHub UI with this closed issue, issue 8150, which is represented by this red square here. And there's nothing else really connected to this work for now. Let's go over another example, this time with one of GitHub's other link types, which is the duplicate. So you can see here someone has reported this problem, message stickers always returns an issue empty list. And this has been reported as a duplicate by the maintainer of the project in that comment as a duplicate of the issue on the right here. So issue 7186 was reported as a duplicate of the issue 7140. And if you visualize this as another graph for a second, Again, with those closed issues represented by these red squares, this is what we kind of get. And notice that the developer maintainer is using that duplicate keyword to automatically create that explicit connection between the two issues, as well as the duplicate issue being reported being created later than the issue on the right, despite covering the same underlying problem. So prior work in software engineering research has focused on these individual link types extensively. The examples I've just shown have explicit link types of either fixes or duplicates, but it's also possible on GitHub to just hashtag mention an issue number, which creates sort of this blank link. And according to prior research done by Chopra et al., about 85% of links on GitHub don't have one of these link types. They're just sort of empty and blank. So, for example, a developer just mentioned the issue number without providing one of the keywords for either the fixes or duplicate link types. So researchers have primarily been trying to classify these links, these blank links, into richer categories than just fixes to duplicates. And different papers have come up with their own distinct taxonomies for doing so, including common link types like a dependency relationship, a relevance between two issues or PRs, and an enhancement relationship. However, we wanted to take this idea one step further. So we're interested in zooming out of this prior very focused perspective on individual issue and PR links. And our research is the first to look at multi-node clusters of multiple issues and PRs as sort of a graph, as I've shown in the visualizations on previous slides. This graph perspective grants us more context, as we simply have more metadata and relationships to examine since we have more limbs to look at. This in turn gives us a richer understanding of the work practices that might be going on in that part of the project, that sub-initiative or that bug fix. For example, we can understand with more nodes and more context if developers tend to break their work up into smaller chunks for this project, or if there's a lot of competition in certain areas. This graph perspective is what we've nicknamed GitHub's PR issue graph. And for the rest of the talk, I'll be showing you what lurking insights about open source collaboration we found hidden in it. But first, you might be wondering, this is a Neo4j conference after all. You might be wondering how we did all of this analysis. So first off, we chose to analyze GitHub in particular as our platform of choice because of its data availability, popularity among open source projects, it's sort of this de facto industry standard, as well as the diversity of projects that were hosted on it. We initially scraped and analyzed 56 projects hosted on GitHub based on a prior sample by Chopra et al. And this sample contained a bunch of projects from vastly different topics. So they contain projects like MLflow covering topics in machine learning, as well as foundational technologies like gRPC web. We downloaded the contents, metadata, and links between more than 90,000 issues and PRs across these projects. From there, we applied a diversity sampling approach, which just means picking the most different sorts of issues and PR clusters that we saw, and got a final sample of 64 connected components, or clusters of multiple issues and PRs. Each of these components had each link manually classified into an extended link type. So we looked into the contents and really understood what the context of collaboration that was taking place there was, and understood sort of if there were any recurring patterns and that we could think of as representing open source collaboration. And we did see some repeated structural patterns, like certain configurations of issues and PRs that we thought were promising to look into further. Next, we imported all of these issues and PRs and their metadata into Neo4j, which is the graph database management software we know and love here at Nodes. And we created these reusable Cypher queries for searching for these collaboration patterns. I'll go more into depth into the structure of each of these queries in later slides, but if you're interested, you can check out the GitHub link on screen here to understand sort of what we're looking at. And on screen, you can see also the Neo4j desktop browser, which we use for prototyping these Cypher queries since it's really easy to iterate and immediately see the results. We find the final scripts with the Neo4j Python driver to collect all of these statistics into our final results. As well, with the Neo4j Python driver and a combination of Bokeh.js, which is a JavaScript visualization tool, and Matplotlib, which is a similar library for Python, we also developed this image visualization and interactive project explorer tool. So you can see here in this GIF that we're dragging around a project, we're zooming in, we're rearranging nodes and understanding the context of like different collaboration patterns that we're seeing here. We use this to streamline that manual coding of all of the 64 clusters of issues and PRs, since it's not feasible to go through the GitHub UI and manually try to recreate these relationships. And we also use this tool in validating our results when interviews with open source developers and collaborators. We'll go more into this in a little bit later. I wanted to get to the cornerstone of our work, which is our workflow type definitions. Let's start by taking a look at a cluster of issues and PRs that we found on GitHub. And this particular example is from the discard.py project. So you can see at the top of the slide here, someone has proposed that we need a rewrite for this invoked parent feature. And this is an issue. And on the bottom of the slide, you can see two people have come up with their own implementations for doing so. You can see that Pseudostock on the left has proposed their own solution, which was eventually vetoed by the maintainer of the project in that second comment as being unsatisfactory. Next, Sebi-Law on the right here comes along and proposes their own PR, which is eventually accepted into the project and merged. Note that both of these PRs reference the original issue with a closes and fixes link type. So you can see Pseudostock on the left uses that closes keyword, and Sebi-Law on the right uses resolves, which are both synonyms under the fixes link type. So if we visualize this in our graph, again, this is what it looks like. We have that issue, that feature request being represented as this red square on the left, as well as those fixes links we saw, in addition to Pseudostock's closed PR on the top here, this red circle, and Sebi-Law's accepted PR, this merged PR in this purple circle. So this is actually an example of how we derived one of our workflow types, the competing PRs workflow type. Each of these workflow types are associated with work practices, and I'll go more into depth into what a competing PR is later, but this might be something like if developers break their work down into small chunks in this area of a project. Each of these workflow types also has a prototypical graph structure, which is making it a really logical application for Neo4j. You can see this prototypical structure on the left here. These graph structures were described as a combination as certain types of constraints because we wanted to represent the layout and configuration of different issues and PRs. So we checked the node type, so issue or PR, the node status, open, closed, merged, the authorship of a node, so if two nodes were created by different people or not, as well as the time in which they were created. And these were modeled in Neo4j and Cypher with a variety of labels, as well as some creative APOC function calls. We've actually defined 9 prototypical workflow types based on the recurring patterns that we saw in our analysis, but I'll just go through a couple today and go through how we identified them and the structure of their Cypher queries. So sometimes developers are eager to offer their own implementation of a task, and they might begin working on someone while not communicating more about their approach or about what they're working on at all, which is what we observed in our competing PRs workflow type. It has this prototypical graph structure of this closed issue connected by fixes link to multiple PRs, and which only one of these PRs is merged. So this represents kind of that this sense of wasted work due to poor communication, because only one of these PRs will eventually be accepted into the project, whereas all of the other implementations kind of went to waste as they weren't being used. Its associated work practice, again, is the sense of waste due to poor communication, but it can also have an implication of allowing projects to identify a best solution. So in that discord.py example I just showed previously, we had the maintainer vetoing a PR because it wasn't a satisfactory approach. And competing PRs, which this discord.py project was also an example of, also allow developers sort of to be more picky and to call out these performance implications that they might not like. So let's get into the meat of the query now. Neo4j makes it super easy to identify like the context and the classes of all the issues and PRs that are connected to a certain pattern of collaboration, which allows us both to find the examples of our collaboration, as is shown in this query, as well as collect the context, so the larger group of these issues and PRs that are surrounding this collaboration pattern. So let's walk through the structure of this Cypher query on the screen. You can see this first highlighted line is a match. So we have this closed issue being connected by a fixes relationship to a pull request. We then make sure that there's only one pull request among this collection of potential spoke pull requests connected to this core issue, and only one of these is merged. We then also check that there are other pull requests that haven't been merged, and in particular that they've been closed, as well as having multiple pull requests. So we don't just have a single link between a closed issue and a merged PR. We then also check that the size of the users list, which is the size of all of the distinct authors of PRs or issues here, is greater than 1, which guards against cases where perhaps a developer contributes a PR, then decides to try a different approach, closes the original PR, and submits a new one, which is eventually merged. In this case, there's not much waste there because this was part of the development process. We also require that this collaboration overall takes place in 1 week, so that 604,000 is 1 week in seconds. And we do this because we want to ensure that there's a sense of real-time competition. So it's not just that a person has submitted a pull request and then has abandoned it, and then someone else comes in a year later to solve the same issue. In that case, there is some sort of waste, but it's not as real-time as we generally saw in other competing PRs examples. So that was the Cypher query to match this exact pattern of a competing PR. Then we used the APOC subgraph all function to then start collecting the context around this particular pattern. So we wanted to get the other issues and PRs that were attached to any of the participating nodes within this pattern. And to do this, we fetched the connected component using the BFS true argument to sort of expand outwards from our pattern to collect as many nodes as possible. We limited the component size that we collected to 50 in order to improve performance a little bit while retaining as much context as needed and was reasonable in the amount of time that we had. Next, we can then use the Neo4j Python driver to connect what we're doing is running the query, as you can see in the Python code on the left, and just importing the results and visualizing that in a graph format. So let's go through another workflow type example. Another painfully familiar issue in open source is that of duplicate issues, where contributors start reporting similar problems that are duplicates of the previous discussions. And redirecting these duplicates to other more established discussions will take valuable maintainer time. This might happen, for example, if a bug goes out in a release, and lots of users start flocking to GitHub to report the same problem, even though it's already been acknowledged by the maintainers of the team. So this is captured in our duplicate issue hub workflow type. Its structure consists of this issue, this leftmost red square, connected via many duplicate links to many other issues, the red squares on the right. And we can see that the duplicate issues were created after this central issue on the left here. This can happen if for example, again, as I mentioned, the bug's going out in release, but also causes this implication of an additional maintenance burden. And this is the Cypher query that we used here. It has the similar structure to the competing PRs query that I just showed. So it matches all of these issue nodes connected with a duplicate relationship label to other issues. An interesting Cypher workaround that we needed here was we needed to check that we wanted to get this list of all of the issues that participated in a duplicate issue hub. And to do that, we sort of had to layer multiple collections. So you can see that we have this known dupes variable per query. So that's done by this collection, collect distinct IDI. Next, in the return line, we then do another collect, which then becomes a lists of known duplicate issues. But then this is a list of lists and we need a set. So we use the flatten method to then create a flat single one-dimensional array, and then use the toolset function to get a set, excluding all of the duplicates, ironically, within the duplicate issue hubs. This is a common pattern throughout our queries, since we wanted to get statistics on how many nodes were participating in certain types of pattern, and so on. Finally, we found that developers tend to sometimes over-deliver in their PRs and addressing multiple issues at once. So here's an example from the gRPC web project, which has multiple. So this single PR is taken from one description, but it's fixing multiple issues that at first glance aren't related at all. And this is generally a negative workflow pattern because when you have unrelated changes in the same pull request, it becomes more difficult to tease apart where the fixes or where the new features in each of these addressed issues comes from, which makes review harder and additional maintenance burden and so on. This is its graph structure. So we have this merge pull request that's connected by fixes linked to multiple issues. Again, this can be both negative and positive. So it might be negative in the case I just showed earlier, where we have multiple unrelated issues being fixed by this PR. But it can also be positive if the issues that this PR is fixing have the same underlying concern. So for example, if all of these issues were part of another duplicate issue hub, and they're all saying we're missing this field in response, the single pull request can then address all of these issues, which might make this pull request more impactful. So this is the structure of the cipher query used here. It has the structure of this pull request, this merge pull request connected by a fixes relationship to a bunch of issues. We then check that we have multiple issues being fixed and we return the results. You might be seeing a pattern here with the competing PRs as well as the duplicate issue hubs. All of our queries generally have the structure of matching a single node-to-node link, then collecting all of the so-called like spoke nodes that are connected to a central node, collecting all of these nodes, running some match against them, checking some condition, and then collecting the central nodes across all of the matches, or collecting all of the nodes altogether to return a list of which issues and PRs were in what type of collaboration relationship. So let's now briefly talk about some of the ways that these workflow types compare to each other. And we wanted to understand how frequently these workflow types happen because it would explain the most common ways that developers worked. We found over 1,000 matches of our workflow types across these projects and 52 nodes that met some basic criteria. So they were in the cluster with other issues and PRs, and they were connected to some other issues and PRs, were indeed in a workflow type match. Most projects had at least one match, and on the left here, you can see this graph of the size of the project in numbers of issues and PRs submitted to the number of workflow type matches. You can see that the largest projects like App VNX Poly and Apache Dubo had the most workflow type matches, so they had around 150 each. But this also, we can see this general upward correlation. So this to us indicated some sort of connection between the maturity of a project and how many contributions it's received to its need for organized collaboration and in turn, the emergent usage of these structured workflow types. This is supported by the fact that the smaller projects that had no workflow types were all relatively small with only a couple hundred contributions each. We had some other insights about the graph and the other attributes as well as the workflow types, but I also wanted to touch on what developers thought. So we validated and interviewed a series of 6 developers who used GitHub and tried to understand how these workflow types in this graph perspective would affect their work. These interviews centered around introducing them to this peer issue graph perspective based on the interactive explorer tool that was preloaded with their project. So for example, if we interviewed the Discord.py maintainer, we would preload it and send them a link with their project so they could just click around and understand sort of how this perspective would help. So developers ended up seeing that these workflow types in this graph perspective would help make better decisions in various aspects of the development process. So one person mentioned that duplicate issue hubs might represent a need for change in the documentation or bug reporting processes. And another mentioned that Divergent PRs could help prioritize review. So Divergent PRs, again, are this one PR that fixes multiple issues. So the idea being that if a maintainer has a backlog of, say, 10 PRs to review, but they see that one is a Divergent PR, they might want to prioritize reviewing that one first because it could have a bigger impact and resolve multiple other issues. As well, developers noted that this workflow type explorer tool could help them better understand the dependencies between different initiatives in the project more visually, which provides valuable context that GitHub and other developer platforms don't highlight on their own. Finally, developers also noted that workflow types are limited because we didn't examine the actual contents of each of the issues or PRs. But unfortunately, this is just a limitation of the approach that we use, and we hope that even surfacing these workflow type patterns can help bring better awareness to these sorts of collaboration implications. So our work does have wide-ranging implications. As I just mentioned, it can help inform prioritization in a project, understanding which PRs might be more impactful to review, and understanding which areas of a project where outsized work or work might present outsized impact. It can also help improve code review practices, as well as project management, again, tying into that sense of prioritization. As well, this tool can help visually identify these areas of wasted work, where there are outsized numbers of competing PRs, duplicate issue hubs, other negative collaboration patterns here. Hirao et al. Have also noted that duplicate and code review tools might be extra helpful if we could more closely analyze the clusters and the issues and the links between particular nodes besides just a high-level understanding of fixes or duplicates. So this is what our approach does. And in fact, we go deeper by expanding the perspective to look at multiple nodes and their contexts at once. Finally, while we've talked about our work with a series of 6 developers, and which we found that our perspective lines up well with what they've experienced, we want to continue talking more with developers, and that's a big next step of our project. So today I've gone over our novel graph-based perspective as well as the sample of workflow patterns that we found hidden in it. As a core plus of our approach here is that because we've created these Cypher queries, our project and our workflow type analysis is super automatable. So maintainers can easily load in their own project and start identifying and curbing unwanted patterns of collaboration. I think one analogy that has resonated well with developers is that you can think of this graph perspective as a Grafana for your collaboration health for the project. It gives you a global overview and impacts and gives you a visual analysis of your impact, as well as giving you early alerts when things might be going south. And yeah, I think that's all for me today. You can reach us here at this email, or you can reach me at hello@emily.ma. Thank you all for listening and hope you enjoyed the rest of this. And if you'd like to stick around, I will be answering, some questions next if we have time.